Hello, I'm Matheus Gadelha, and I will present our work on learning point cloud representations using approximate convex decompositions. This work is a collaboration with Aruni Roy Chowdhury, Gopal Sharma, Evangelos Kalogerakis, Liang Liang Kiao, Eric Learn Miller, Ray Wang, and Subhranshu Machi. Everyone is from UMass Amherst. Consider a set of point clouds representing various shapes. For example, here we have a lamp on the left, a chair, an airplane, and an office chair on the right. Now, imagine that we want to do part segmentation. In other words, for every point in a point cloud, we're going to assign a category corresponding to one specific part. For example, if you take the airplane, imagine that we want to classify every point in the airplane as belonging to the body, to the wings, to the engine, or to the tail. So, if you want to train a model to do that, you actually are going to need a lot of data because you need to have a label for every point in a point cloud. So that's why we want to learn how to build discriminative models for point clouds using as few labels as possible. In reality, we have access to a set of unlabeled shapes and also access to a much smaller set of labeled shapes. Since the set of unlabeled shapes is much bigger than the one of labeled shapes, a reasonable question to ask is how can we use those unlabeled shapes to improve our model? Our research is inspired by decades of work in geometric decomposition techniques. More specifically, we're interested in a class of techniques called convex decomposition. The main idea of convex decomposition is to decompose polygons and polyhedra in a smaller set of convex components. Let's take a look at an example. If you consider the polygon on the screen, you can imagine that you can decompose this polygon in a set of convex parts. This procedure is called exact convex decomposition, and it's going to yield a result similar to what we have here. The different colors mean that those are different components. However, if you take a look at the left part of this decomposition, you're going to notice that there are too many parts, and that's probably not what we want. It would be nice to have a single part that is representing all that structure. That's where approximate convex decomposition comes in. So in the end, we don't want exactly convex components, but we want something that's going to be convex up to an epsilon margin of error. So we have this shape that now decomposes in three parts. As you can see, the blue part and the yellow part, they are not really convex, but they are close to it. And this is a very useful property if you want to apply this technique on real shapes. Okay, now we can go back to the examples that we saw in the beginning of the presentation. Each point cloud now can be processed using ACD, and that will yield a set of approximately convex components seen here on the screen. Notice that this procedure is fully automatic and does not rely on any extra human annotation. If you look at the components computed by ACD, we can directly compare with the parts annotated by human annotators. You'll notice that even though there's not a direct correspondence between the parts computed by ACD and the parts annotated by humans, the boundaries roughly correspond to each other. For example, if you look at the airplane, the wings are actually represented by multiple ACD parts, whereas the human labeled the wings as a single component. However, the boundary between the wing and the body is still there, and the same can be thought of for the engine and for the tail of the airplane. If you can train a model to learn how to perform approximate convex decomposition on point clouds, the features that we learn by doing that are probably very useful in other tasks, like for example semantic particle segmentation. Let's take a closer look at how our method works. In the bottom, we have a set of shapes labeled by human annotators. On the top, we have a set of unlabeled shapes that we're going to artificially generate some parts by using approximate convex decomposition. Then, we're going to use those two sources of supervision to train a point cloud neural network. You can use any architecture that you want, like PointNet, PointNet++, or DGCNN. We have a pretty good idea on how to train the network using direct supervision. On the other hand, we don't have a good idea on how to train a network to perform ACD. There are some important differences in those two training setups. So first, the parts of every shape, they have some semantic meaning. If you take the airplane, you're going to see that the airplane, every point is either a wing, an engine, a tail, or a body. If you have a chair, every point in the chair is a seat, a back, legs, armrest, and so on. Our goal here will be how to train a neural network to compute per point embeddings that, for example, when clustered, are going to yield something very, very close to what ACD is doing. So if those embeddings are going to be trained, you're going to learn nice features on your neural network, and those features can be used for a bunch of other tasks, like for example part segmentation. Let's take a look on how to train a neural network to perform ACD on point clouds. First, let's establish some notation. Consider a point cloud X, a pair of points Pi and Pj, and a set of convex components C. Let's also define a function gamma that, given a point P and a set C, is going to tell us which component in C contains the point P. So our loss function is actually quite simple. If Pi and Pj belong to the same convex components, we want the embedding of these points to be as close as possible. If Pi and Pj belong to different components, we want their embeddings to be as far as possible up to a margin m. So for example, if you want to train a neural network to perform part segmentation, your final loss is going to be a combination of a cross entropy loss plus lambda times the pairwise loss that we just defined. Now let's take a look at some results. We start with the unsupervised shape classification in ModelNet 40. This benchmark consists of training the network using ShapeNet shapes and then using the features to train a linear classifier that will perform the classification. So if we train our neural network to perform ACD and use those features to train a linear classifier, we're going to get 89.1% accuracy, which matches the current state of the art. If we further add a reconstruction component while training those features, we achieve 89.8% accuracy. We also analyze our method in few-shot part segmentation. In this setup, our neural network is trained to perform both part segmentation and ACD. As we can see, when you use 5% of the labeled data, our model yields 2% improvement over the state of the art. When using 1% of the labeled data, our model yields 7.5% improvement. Here are some qualitative results of the few-shot part segmentation. As you can see, the model that's trained to also perform ACD is capable of recognizing some parts that are completely missed by the baseline. For example, if you look at the airplane on the left, the engines are missing. If you look at the rocket in the middle, some details are also missing. Or if you look for the rocket on the right, you're going to see that the wings and the tail are not correct. Finally, we analyze the effect of ACD self-supervised training on different backbone architectures. All the results that we showed so far are using PointNet++, but as we can see from this table, if you use DGCNN as a backbone, you're also going to see similar improvements. On the unsupervised classification benchmark, we're going to get 14.1% improvement over the baseline when using ACD pre-training on DGCNN. On 5-shot segmentation, the improvement is of 9%. So in this work, we show that training networks to compute ACD is an effective self-supervision task. It's useful for shape classification, but is particularly effective on few-shot shape segmentation. An interesting area of future research is to analyze if other shape decomposition techniques also yield good supervisory signal. Please check our paper on arXiv and our webpage for extra results and code. Thanks for watching.